Now we will see capacitance when a dielectric of thickness T is inserted. Here you can see that the dielectric is not having the total thickness D. Now the thickness is reduced. That means dielectric is occupying only a thickness of T in this width D. This part it is air, and here also it is air. So in between the plates only T thickness will be experiencing an electric field E, and this space, that is D minus T, will be experiencing an electric field E0. E0 means electric field when air is present. So only for this thickness region it experiences an electric field E, and this regions where the dielectric is not present, it experiences electric field E0 as air is present. So that is written here. Potential difference is equal to electric field into distance. That is a expression. So for dielectric, electric field is E, and thickness, dielectric thickness is T. Then there is some space which is having air. So there the electric field is E0. 0 represents air or vacuum. And here the thickness is D minus T. So now we are going to make a change. Already we have written in the previous topic E is equal to E0 by K. Okay, so electric field when dielectric is present, it will be less than electric field when air is present. It is less by a factor 1 by K. Okay, so here instead of E, we are substituting E0 by K into T plus E0 into D minus T. So here you can see both the terms are having E0. So we can take E0 out, E0 into T by K plus D minus T. What is E0? E0 is the electric field when air is present. So that is sigma by epsilon 0. So sigma by epsilon 0 into T by K plus D minus T. Now this is the potential difference. Now we are going to write the expression for capacitance. Capacitance is Q by V. What is Q? Q is equal to sigma into A. That is surface charge density into A. V, this value you have to substitute. So sigma by epsilon 0 T by K plus D minus T. Now here sigma and sigma will be cancelled. You will get C is equal to epsilon 0 A by T by K plus D minus T. This expression is actually needed for our numericals. So if the dielectric slab of thickness T minus D is introduced between the plates of a capacitor, this T and D, when it is equal, here you can see T minus D, D minus T term will become 0. So you will get K into epsilon 0 A by D, K into C0. This we have already derived in the previous part. Now capacitance when a conductor is inserted. When a conductor is inserted, the electric field inside the conductor will be equal to 0. That we have already learned in chapter 1. So this electric field here, it will be 0. So only electric field will be in the region where air is present. So that term will be changing. We will see that term. So again deriving like what we have done, E0 into D minus T plus 0 into T, E0 into D minus T. E0 is substituted by sigma by epsilon 0 into D minus T. And Q is equal to sigma A. C is equal to Q by V. Q, instead of Q we are substituting sigma A, and instead of V we are substituting this value sigma by epsilon 0 into D minus T. Sigma and sigma gets cancelled. You will get epsilon 0 A by D minus T. Now when the conductor is having the thickness T is equal to D, this will become epsilon 0 A by 0. Denominator 0 means that quantity is not defined, or we call it as infinity. So capacitance will become infinity. So that is also a sub case which is not will not be asked for essay question or anything. It is an application which we have said. Now we will see combination of capacitors. We have already seen the combination of resistors. Resistors can be combined in two ways. One is series combination, another one is parallel combination. So here this is a series combination of capacitor C1 and C2. Already we have learned that for series combination, the current or charges will remain the same, but the potential difference will be different. So here the potential drop is V1, here the potential drop is V2. So the total potential drop which we have applied, it is a sum of V1 plus V2. And according to the equation for capacitance, we know that V is equal to Q by C. or C is equal to Q by V. So C is equal to Q by V. So from that we can write V, you bring it here, C you bring it here. So we can write V is equal to Q by C. So here in the first case, V1 will be Q by C1. Charge will remain the same because it is series combination. Current is the same. So charge is the same. Now for the second one, Q by C2. So here the total potential by charge is equal to this Q we are taking common. And that Q we are taking to left side. V by Q is equal to 1 by C1 plus 1 by C2. What is V by Q? V by Q, it is 1 by C. So Q by V is C. So V by Q is 1 by C. So you can write 1 by C is equal to 1 by C1 plus 1 by C2. This is the case when we are connecting series. It is just the opposite to that of a resistance. In the case of two resistors, R is equal to R1 plus R2 in series. And here, but in series, capacitance 1 by C is equal to 1 by C1 plus 1 by C2. This we are getting in parallel in the case of resistor. So for the capacitor, it is just the opposite. Now if n capacitors are connected in parallel, 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. 1 by Cn. So this we have learned. Now we will see capacitors in parallel. So here you can see two capacitors are connected in parallel. In the case of a parallel combination, potential difference will remain the same, but the charges will be different. So here the charge will be Q1, here the charge will be Q2. So the total charge will be the sum of Q1 plus Q2. But we know that Q is equal to C into V. So here the total charge Q is equal to C into total potential difference, and Q1 can be written as capacitance of the first capacitor into the potential drop V. Here capacitance of the second capacitor into V. So here you can see that V is there in all the terms. We can cancel that. C is equal to C1 plus C2. So the effective capacitance of n capacitors we can write as C is equal to C1 plus C2 plus etc. up to Cn. So this is the case when n capacitors are connected in parallel.